We're going to finish out chapter 15 by looking at some calculations of the equilibriums of weak acids and weak bases. So chapter 14, 15, we move through this week. Those modules are due Sunday, the 13th at midnight. I will also have a review session Sunday, 8 to 9 p.m. Any last minute questions, keep using the discussion board, keep posting your questions. I'll do the best I can to put together maybe a little bit of a review video or work through the problem that you have a question with. As I said in class today, Sarah and Meg both have office hours. They both said that no one's really showed up to office hours, so please take advantage of that time. They're there to help you, so that's what they would like to be able to do, and they would be more than happy to do that with you. So last class we looked at acid-base, and we introduced, what is an acid and what is a base, and we came up with a very generic Bronsted-Lowry definition of an acid as anything that can donate a proton, where a proton, is H+. And a base is any substance that can accept a proton. So in this case, ammonia behaves like a base. It accepts a proton from water. That means water's donating a proton, and that makes water an acid. And so in the course of this reaction, ammonia accepts a proton, behaving like a base, making the conjugate acid ammonium. The other product from this reaction is hydroxide. Water behaves like an acid. It donates a proton, forming the conjugate base, hydroxide. We also looked at how we determine the pH of a solution, pH equals the negative log of hydronium ion concentration, where hydronium, or H+, those are used interchangeably. Both of those mean the same thing. And it is lowercase p, capital H, because that lowercase p means take the negative log of hydronium ion concentration. We also found out we could reverse that calculation if we know pH, but we want to find hydronium. Well, that equation is hydronium concentration equals 10 to the negative pH. And we also looked at these negative log scales that also apply to hydroxide concentration. So we could also find the pOH of the solution, or a pKw. We can apply the negative log to a few different concentrations and values during this chapter. And the same equation that works to go from pH to hydronium concentration also works for pOH to go to hydroxide concentration. So again, if we know pOH, we can find hydroxide. If we know hydroxide, we can find pOH. We can go both directions with those calculations. And the last thing we looked at, the last relationship that we looked at, is that pH plus pOH always needs to equal 14. So if we know the pH of the solution, we automatically know the pOH of the solution. Or if we know pOH, we can find pH because the sum of pH and pOH always needs to equal 14. So that was the last relationship we looked at last class. Today we're going to look at how to calculate the pH of a concentration of a strong acid in solution and a weak acid in solution and a weak base in solution, So the strong acids that we talked about last class, I said definitely get to know the strong acids because any other acid is a weak acid. If it's not a strong acid, it's a weak acid. There are much fewer strong acids, so it's much easier to know the strong acids than it is for the weak acids. The strong acids are strong because they ionize completely. That's what characterizes a strong acid. It ionizes completely. So strong acids are, good electrolytes. Because they ionize completely. They are not reversible. There is no equilibrium. So a strong acid like HCl would react in water, to form hydronium. and chloride. There is not an equilibrium, right? It's actually just a one way, so one giant arrow pointing to products. There is no equilibrium with this reaction because HCl is a strong acid. It ionizes completely. So what that means is the concentration of HCl I put in solution equals the concentration of hydronium I have in solution. That makes it easy to find the pH of these solutions. Right, so let's take a look at that. How would I calculate the pH of a solution of a strong acid? So if I've got 0.1 molar HCl in solution, right, and again, HCl is a strong acid, so I put 0.1 molar in, all of it ionizes. So what that means is it all ionizes into hydronium and chloride. That means I've got a 0.1 molar solution of hydronium in solution. And at this time, you might be thinking about, well, we also looked at the auto-ionization of water. Should I have to worry about that concentration of hydronium as well? Well, if you remember, when we did the auto-ionization of water, we determined that the concentration of hydronium from the auto-ionization of water was 1 times 10 to the minus 7 molar, right? That number is incredibly small. It's so much smaller than 0.1 molar that no, we don't have to worry about the concentration of hydronium from the auto-ionization of water. The concentration of hydronium from HCl is so much greater that the concentration of hydronium from the auto-ionization of water will have no impact on the pH of that solution. That means we can calculate the pH. pH equals the negative log of hydronium directly from the concentration of HCl in solution. So the pH of this solution would be the negative log of 0.1 molar of hydronium from the 0.1 molar HCl. So the pH of this solution is 1. So to determine the pH of a strong acid solution, it's very easy. Because it's a strong acid, it ionizes completely. We can find the pH of that solution by taking the negative log of the concentration of that acid because that'll equal the concentration of hydronium in solution. Strong bases are much the same, so they're group 1 and some group 2 metal hydroxides. But the important characteristic is that they ionize completely. Just like strong acids, strong bases ionize or dissociate completely in solution. Right, we could look at sodium hydroxide, a common strong base. It's a solid, we put that into solution, we add water, and I'm going to get sodium aqueous and hydroxide aqueous. So just like the strong acids, strong bases ionize completely. 100% of what I put in is going to go to form sodium cations and hydroxide anions. So group 1 hydroxides, so lithium, sodium, potassium, rubidium, cesium, and some of the group 2 metal hydroxides, like calcium and barium, right? Most of the other metal hydroxides are not soluble enough to be considered strong bases. But again, it's easier to know the strong acids and the strong bases because any other acid we look at, any other base we're going to look at is going to be a weak acid or base. So here's a calculation for you. Calculate the pH of a solution with the concentration of 1.4 times 10 to the minus 4 calcium hydroxide. And I'll give you a hint about this calculation. I'll give you that when calcium hydroxide ionizes, right, we can write out that reaction of solid calcium hydroxide ionizing. It's going to go into solution to generate calcium 2+ and 2 hydroxides. So the key for this calculation is that for every 1 calcium hydroxide that ionizes, the solution will gain, right, we're going to form 1 calcium and 2 hydroxides, right? So we produce 2 hydroxides for every 1 calcium hydroxide that went in. So that generates twice the concentration, generating twice the concentration. So I have a concentration of 1.4 times 10 to the minus 4 molar calcium hydroxide. Right, for every 1 calcium hydroxide, I'm going to generate 2 hydroxides. So multiply that concentration by 2, and the real concentration of hydroxide is 2.8 times 10 to the minus 4 molar. Now I can find the pH of this solution. So I'm going to start with POH because POH equals the negative log of OH, and that's what I have. I have the OH concentration right here. So POH equals the negative log of 2.8 times 10 to the minus 4. Take the negative log of that. The POH of this solution equals 3.55. And the last calculation, I know pH plus POH equals 14. I want to find pH, so I know pH equals 14 minus POH. pH equals 14 minus 3.55. The pH of this solution is going to equal approximately 10.45, right? Ask yourself, does this number make sense? I'm calculating the pH of a basic solution. I know the pH of a basic solution should be greater than 7. I calculated a base pH of 10.45. That's greater than 7. This is clearly a basic solution. But the key and the reason why I asked this question this way was we have to remember how calcium hydroxide ionizes. We have to remember some of those things from first semester, how things come apart, how many ions do I generate, and what does that mean? That means I generate twice the concentration of hydroxide in solution, and that's how I'm measuring POH and pH. So I need to take into account that I have twice the concentration there.